Hey everyone, today we'll be looking at 322, that is a coin change problem from Neetcode list of 1D dynamic programming. So yeah, let's try to solve this and set the timer. You're given an integer array coins representing coins of different denomination. Okay, and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coin, return -1. You may assume that you have an infinite number of each kind of coin. Okay, 1, 2, 5 amount equal to 11. So 5 plus 1 equals to 3. Okay, so how can we go about solving this question using 1D DP, like using dynamic programming? Mm, I'm thinking that we can recurse on this. There are n number of combinations, not n number of combinations. If you see, we can use 1 11 times. 2, if we just use 2, then we don't have any chance of getting to the answer because it will exceed. And 5 also is the similar. So at every stage that we have 1 and 2, what do we need to do here? Let me open up the whiteboard. Okay, so coin change problem 1 to 5 is given to us. What can we do in that case? We can take index of 0 and not decide to take index of 1, index of 0, and then jump on to the 2. Excuse me. So okay, so what we can do here is that I was thinking of taking 1 and add that to 1. So the base case would be at any point if the amount is greater than 11, we should return 0 in that case. And anytime if we find 11 amount to be 11, then we should send. So for using recursion, I believe that we have to send each guy for let I is equal to 0, I is less than coins dot length. And instead of directly jumping into the solution, we should ask the interviewer whether the coins be length, can it be 0, or will we always have some coins? Okay, and can the coins will be always in a positive integer? Okay, and the range of the amount 10 raised to 4. Got it. And what we need to send here to DFS is that we need to send the 0, which is the start price, and coins of I, which will the price of it, and let minimum is equal to, let's say, number dot max, as we have to find max, safe integer. Okay, so we have this, and what we need to do is mat dot min, and yeah, we need to compare it with this guy, and let, oh no, sorry, we have to set the min to this and return minimum number that is required. So we can okay, yeah, so we can do this, and we should be returning min, but how will our function DFS start and then current, so let's call it total. If total at any point is greater than amount, then we should be returning 0. If total is equal to amount, then that point we should be returning 1. Okay, so here's the main part. What we have to do is, for every so I believe I have to again let I is equal to 0, I is less than coins dot length I plus plus. I have to do this, and I have to, you know, start. So this is our start, right? So how this start will affect how we go about traversing this guy. Because so what we can do is we can have DFS and then coins of I. We'll send coins of I, and basically we'll add total plus coins of I to it. Yeah, we'll do that. We'll add coins of I to this and we'll send it. So after 11 times it will return 1. So what should we do about this one? We should we we should also keep a track of minimum number, or so we are sending 1, right? We are sending in 1 as soon as we reach there. So we gotta add that to the count. So this is no longer making sense to me, but let's try it out. Okay, so what we need to do is we have, what did we have there? 1, 2 and 5, right? 1, 2 and 5. So what I did was I took 1, then I did 1, 1. I added 1 11 times. So it will keep. So 1 plus 1 plus, so here it's 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. As soon as I reach here, 10 and 11, as soon as I reach here, I send back 1. Okay, and then here so I know that I got 1. What should I do in this case? What should I do in this case? Should I keep continuing this track, or so I should be adding that 1 all the way up to, right? I should be add that 1, and then this becomes 2, then this becomes 3, this becomes 4, 5, 6, 7, 8, 9, 10 and 11. If it is not 1, then we can, so this guy returns 1. What we gotta do is count let ans is equal to, if ans is greater than equal to 1, then count is equal to 0. So what we'll do is we'll count plus equals to 1, sorry, ans, and return count, right? So doing this, we've got 1, but when 2 comes in, but okay, so then we'll do the same with 2. So 2 comes in, 2, at this point it's 4, then 2, then 6, then 2, 8, then 2. Actually, basically when we send 2, we won't be directly jumping on, so 2 will start with 1, then we'll go on with 1. So this would send out to be or if not, if we cannot return, then return 0. Okay, minimum, right? Okay, and okay, I guess I should look at the editorial, because it's pointless of me going around. So okay, another panga. Okay, no worries.
Hey everyone, welcome back, and let's write some more Neetcode today. Today let's solve another classic dynamic programming problem, coin change, and we get a pretty simple description. So we're given a list of coins of different values, and we're also given a total amount of money that we want to sum up to, but we want to use the fewest number of coins possible to make up or to sum up to that amount. And it's possible that that amount of money cannot be made up with any combination of the coins that we have, and then we want to return -1 if that's the case. And luckily for us, we're actually given an infinite number of each coin. So in the first example, we have coins of value 1, 2, and 5, and we have infinite quantities of these coins. The amount that we want to sum up to is 11, and basically, just look at this. What's the fewest number of coins we could do? Well, of course, we want to use a 5 because it's the biggest one. We can use another 5, and then we just need a 1 left if we want to sum up to 11. So in this case, you can see we only needed 3 coins. This is the fewest number of coins we needed, so we can return 3. In the second example, we have a coin of value 2, but we want to sum up to 3. We can try 2 plus 2, but we know that's 4, so we went over 3, so there's no way to possibly sum up to 3, so we return -1. There's no possible solution. So your first idea might be, can we just be greedy? Is the problem that easy? Can we just be greedy? And let's look at this example. So let's say these are our coins 1, 3, 4, 5, and we want to sum up to 7. So when I say greedy, I mean, okay, we want to sum up to 7. Let's just start at the biggest coin we have. So let's start at 5. So now let's look at the biggest coin again, 5. If we add a 5 here, we know we're going over the total amount 7, right? So we don't add another 5. Well, let's look at the 4. Well, we know 5 plus 4 is also going to be more than 7. 5 plus 3 is going to be more than 7. Okay, but we found a 1. Luckily, we have a 1. So let's add 1 to it. Now we're at 6. So let's add a second 1. Now we got to the sum 7. So we basically went down from the biggest, smallest coin values, right? That's what I mean when I say greedy. Let's pick the biggest one possible first. So notice that this took us 3 coin values, right? So our result in this case would be 3, but is that the minimum amount of coins? The answer is no, because, just looking at it, we can tell we got a 3 and we have a 4. 3 plus 4 is 7. That means the minimum amount of coins is actually 2. So this is a counter example. We cannot be greedy if we want to solve it. So the next thing you might try is like a brute force solution, right? So to do the brute force solution, we need to implement some kind of depth first search or backtracking solution, right? So let's look at the same example, 1, 3, 4, 5, and amount sum to 7. So what would a backtracking solution even look like for this problem? Well, it's going to be brute force, right? So we have 4 coin values. So that means in our decision tree, we have 4 possible choices. We can choose a 1, we can choose a 3, we can choose a 4, or we can choose a 5. In this case, the remaining amount would be 6, because 7 minus 1 is 6. In this case, the remaining amount that we have to compute would be 4, because we're taking 7 minus 3, which is the coin that we chose. So we get 4 as the remaining amount, right? In this case, we would have a 3, and in this case, we would have a remaining amount of 2. So since none of these are 0, once we get to 0, we know that we've computed the total amount that we want. But right now, we have to continue going, right? We have to continue doing the brute force approach. Let's start at this side right now. So we still have 4 coins, right? We have unlimited quantity, so we can choose the coin 1, we can choose a 3, we can choose a 4, or we can choose a 5. If we choose a 1, we'll have a remaining amount of 1. If we choose a 3, we're going to get a -1. What does that tell us? That tells us if we chose a 5 coin and we chose a 3 coin, then we get to a negative value. That means 5 plus 3 cannot be the amount So we don't have to keep searching here. We can stop, right? We got to a negative value. If we keep adding values to it, it's just going to become more and more negative, right? And you can probably notice that since these values are even greater, 2 minus 4 is going to be negative 2, 2 minus 5 is going to be negative 3. So we can't go down these paths either. We don't have to search them anymore. And so now here we're going to see, okay, we can choose a 1 coin. Of course, we can choose a 3, 4, and 5, but we can see from here that that's not going to work. That's going to lead us to a negative value anyway. If we choose a 1 over here, then we know we're going to finally get to a 0. So this is what we want, right? We took a 5 from up here, we took a 1 from over here, and we took a third one, right? So then if we count how many coins we chose down this path, we know we get 3 coins, right? And we get to a 0. So of course we don't have to keep searching anymore. So we found one possible way where we can sum up to the amount 7. We know it has 3 coins, which, from the previous example, we know that that's not the minimum amount of coins, but we found an algorithm that at least tells us a possible solution. So we can kind of keep track of that. The minimum coins we can set to 3. So now I'm going to show you what happens when we go down this tree path, even though we know that the solution is actually 3 plus 4, which is 2 coins, which either of these is going to get us to the correct solution. I'm going to show you what happens when we go down this one anyway. So we can choose a coin 1, 3, 4, or 5. So if we go down this path, we will have a remaining amount of 5. Here we'll have a remaining amount of 3. Here we'll have a remaining amount of 2. Here we'll have a remaining amount of 1. Do you kind of see how we're taking the original problem, which is 7, and then breaking it down into sub-problems like 6, and then breaking it down even further into 5? And not only that, we have sub-problems, yes, but do you also see that these sub-problems are repeating themselves? Here we have a remaining amount of 1. Here we also have a remaining amount of 1. So do we even have to compute this path? Because we already know if we have an amount 1, it takes only a single coin for us to be able to reduce it to the amount 0, which is what we're looking for. So since this subproblem repeats, I don't have to compute it. I can just borrow from over here. So in that case, we see the same thing happened though. We use a coin 1 and we get 0, and we see that, okay, it took 3 coins for us to get to 0, right? We took a 1, a 5, and another 1 from over here. So basically we got the same thing that happened over here, just in a different order. And just to make this a little less messy, I'm just going to tell you that none of these are going to lead us to the optimal solution. So now let's look at this case. We have a remaining amount of 4. How many coins does it take for us to get an amount 4? Well, let's brute force it. Let's check every possible combination. Here we'll get a 1. Here we'll get the value we're looking for, 0. That's great, but let's just look at this last one. With 5, we'll get a -1, meaning we can stop searching. So this is awesome. We got a 0, and let's count how many coins did it take us to get to this 0. We took 1, 4, and we took a 3, so this path is only 2 coins long. We see our minimum is currently 3, but we can actually replace this now with a 2, because 2 is the minimum number of coins needed to total to amount 7. So we know this is the correct answer, but let's just see what happens with the remaining stuff. So first, let me just look at this 1. We see we actually already solved this subproblem over here, so we don't really need to solve it again. We know it takes 1 coin for us to go from 1 to 0. And what about this 3? Okay, well, we can do the same thing, right? 1, 3, 4, 5. And I'll just tell you, from here, we're not going to find the optimal solution. Going from 4 to 3 and more, that's going to obviously be more than the current minimum of coins that we have, which is 2 right now. So this is not going to lead us to the correct solution, but you see that once we compute this stuff, then we have one last subtree over here, right? This.
Guys, I think I will take more than what I anticipated. So I guess it will take an hour or so, because I think I'm not following with this video. I need to watch some other video to really grasp what is going on. So I'm ending the stream right now, but I'll be back and hopefully next time we can solve the problem, or again we'll keep striving to get better. Okay, cool. See you in the next stream.